The next thing that's the important pieces. We've seen carefulness, significant figures. We've seen how the size is different for math, and so those are the scientific notation. What about the what about the units? Units in the world were important to come up to be describing something. So if I say, hey, what's my mass? If I'm 100 kilograms, or somebody else says I'm 220 pounds, that you can compare those between countries. The standardization of measurements so that one person could communicate and deal with another person at another part was critical. And then about the same time, our country had just finished our revolution, 1770s, that France was going through something similar. And the big reason for it is that people that lived close to the king, and the king could get out and measure their land, were being taxed more than people that lived far away. And so they wanted to come up with a system that everyone would be fairly measured. And of course, that's what the market depends on. So they started by coming up with the first unit that should be used in the metric system. They said, we need to find something everyone could measure so no one could cheat each other out. The French decided at the time, who did come up with the metric system, is that we'll take 1/10,000,000th of the distance from the equator to the North Pole as a standard because it's found in nature. So if we just go from the equator to the North Pole, that's 10 million meters, and 1/10,000,000th of that can be determined. Now it's fascinating because it took 3 generations to figure out what that distance was of cartographers, a father and a grandfather, a son, grandfather, a dad, and a son figured that problem out, and that's what started the whole French Revolution, is the equality of measurement. And as people said, well, we don't want that to be imposed on us by a dictator or a king, they chose then to go towards what they saw would happen in the United States. Not only was the meter then chosen as a very physical distance that anyone could determine, so were some of these others. And these are the basic units. There are basic units that are called fundamental because you have to have something in nature you compare them to. You can't get them any other way. Now, as technologies have improved, something like the meter, for instance, we don't go out and measure 1/10,000,000th of the distance to the North Pole from the equator anymore. We use something that's may not seem easier, but we can replicate in a lab. What the time is how far light travels in almost 1/3,000,000th of a second. How they do that is still beyond me. I'm not sure if somebody's out there clicking on a stopwatch and seeing how far it travels, but they time how fast light takes, to go, one certain distance, 1/3,000,000th of a second, and that's the now definition of the meter. The gram was certainly similar. This one, they couldn't come up with something standard in nature, so they defined it actually as a cylinder of certain kind of metal in a certain size with a certain radius, and that's what the gram or the kilogram, both of those are stored as standard units back in France. The second was defined originally as 1/886,000th of a day. It's 12 hours in a day, 60 minutes in an hour, 60 seconds in 60 seconds in an hour, a minute. So the second has been changed to then say, if you look at a radioactive cesium mass, it creates a little fountain of particles that come off of it, and it's called the cesium clock. And the time it takes to give off so much mass is the second. So every second it gives off a set amount of material. And so it's called the cesium mass second. The amp is how much current flows through a electric wire. So they can measure those usually just because it creates some magnetism. They can measure how much electricity goes through a wire, and it's a set amount that can go through. So an amp is how many electrons basically pass through a wire in a given time. That's a unit called the amp. You may realize temperature. Temperature is a unit which you would see at least in Celsius, because you've seen that from the metric system. And it was based on originally it was based in the metric system for melting point of water and boiling point of water. Kelvin has taken over because water, you can get colder temperatures than freezing water. And so they said, well, we really should have something because a lot of calculations were using temperature in them, and what happens when you get to the negative side of zero, it was goofing up some of those calculations. So they said we need to get to a place where there is what temperature measures is really just the motion of the molecules. If your hand is very sensitive to it, you can actually touch 2 different things, and you can tell which one's cooler because the motion of the molecules isn't bumping in your hands as much. That's a cooler object. Well, they said, let's get to a place where there's no motion, and that motion is 0 degrees, and that's the absence of all moving particles, so that it would be 0 degrees Kelvin. It's 270 degrees below 0. Very, very cold. Kelvin is the same size as Celsius because they thought that was a very convenient size. 1/100th of the distance between freezing and boiling water. And that's still the size, but it's just got 273 more degrees to get down to absolute zero. And so that's why Kelvin is established. Candela is how bright your lights are, how bright stars are from solar systems in different distances. And the candela, I think it's lumens, I think. Don't quote me on that in terms of the English system as a comparison. And then the magnetism is Gauss. So you should know, at least be familiar with those units and what they measure over here. If you can do that in terms of just recognizing them, I've got some problems on the worksheet below that can. Now you should also recognize there are a couple of units that I missed. These are fundamental because there's no other way to reproduce them. But there are some units that would use a combination of those I've mentioned, and one should be very familiar. For instance, volume. A liter, which you go and buy soda from in bottles, is 1/10 of a meter by 1/10 of a meter by 1/10 of a meter. So it really has a nickname for this relationship. 1 decimeter, 1/10 of a meter by 1/10 of a meter by 1/10 of a meter. All these others down here are also just combinations of units above. They do get their own unit, like the liter is an L. Degrees Celsius is the same thing as a Kelvin in size, but you just add 273 to it. But here's a few others, like a Newton is how much push you could exert. It's the push that 1 kilogram mass exerts when it falls a meter faster every second. That's the Newton. Pascal is how much pressure is exerted over an area. Joule is how much energy and heat. Okay, we call them BTUs in the English-British unit that we use in the United States. The watt is how much power gets charged for. You've seen 60-watt bulbs, 80-watt bulbs. That's how much you're getting charged for the electricity to pass through the light. That's different from candelas, which is how much brightness comes off the light. We typically assume that light's brightness is due to the wattage. It's not. That's how much electricity runs through it. Nowadays, you can get these other lamps that are much lower wattage, but still give the same brightness. And that's the difference, because brightness is measured by candelas. What you get charged for running that light, the electricity through it, is called a watt. And the last one is Coulomb, and that's how much charge is there. So electric lightning bolt, for instance, would have several, I'm not even sure, I'll have to look those up, but it's dozens and dozens of coulombs of electrons. It's like a bucket of electrons. Whereas the amp up on top, which is current, is how many are running through the wire at one time. The bucket, in terms of volume of electrons, number of electrons, the current, which is how many can pass through a certain area. Your house, you want to keep the electrons to a minimum because the faster they run through there, the more they shake the atoms. What do we say shaking atoms was? Temperature. So if you push electrons through a wire or your stove on your stove, it gets hot because they're bumping the atoms, they're moving faster and faster. So Coulomb is how much charge is there, and you usually measure it by opening the gate of a switch and how much flows through for a second, and then shut it off, and that's how they count electrons. A little like herding something, like cattle or something through. So take the time to answer the next part of the worksheet, and then we'll come back to then talk about the prefixes.